To simplify the calculation of the probability, or equivalently the cross-section, because both are proportional to each other, let's assume that electrons are actually distinguishable particles, and therefore we don't take into account the exchange term, we just have the direct term in the amplitude, and we need to take its modulus squared. This is the amplitude we obtain from Feynman rules. So we are going to take the modulus squared of this amplitude, and in particular we are going to focus on the terms with the spinors and the gamma matrices. Note also that to simplify the notation, I didn't put the spin degrees of freedom explicitly in the spinors, but this is implicit and we will restore it later. Remember that these are just C numbers, therefore to get the modulus squared, we take the complex conjugate and we multiply by the original term. Note that I have to change the Lorentz index, so if initially I had mu, for the second term I need to have another Lorentz index and I choose nu. So let's look at one of these terms. Remember some basic properties of spinors and gamma matrices. So we see that the effect of the complex conjugation is to swap K and P. The brackets here are not necessary, but they are just here to remind us that these are just C numbers. And therefore I can swap two of those if I wish. And I will do that in order to bring all the P dash K dash on the left and all the K P on the right. So far I have left the spin degrees of freedom implicit. It's now time to treat them explicitly. And we need to think of what we want to measure or to calculate. Usually what we have access to is what we call a non-polarized cross-section. Usually we don't know what is the spin of the incoming particles, and therefore we have to take the average over their spin. So that's why we have half of sum over s and half over sum over s dash, s and s dash being the spin of the incoming electrons. And often we are not able to measure explicitly what is the spin of the outgoing particle, and therefore we need to sum over all possibilities. And that's why we have a sum over r and r dash, the final spin of the particles. So what we are summing is the probability for each of these terms with ss dash becoming rr dash in the final channel. There are other terms in the expression for the cross-section which do not matter right now, and that's why we just have a proportionality here, and therefore I can also get rid of the 1/2 factors. So what we need to do now is to restore the spin into this expression and sum over all the spins. But we also see that we have the dash term in the left and the non-dash term in the right. Therefore, we will have a sum over s dash and r dash are only going to affect the first two terms, while the sum over s and sum over r is going to act only on the right part. So this is just a product of two terms which are very similar. So we are going to only consider one of these terms. Remember that these are line spinors, column spinors, and 4x4 matrices. It's convenient to express this product of spinors and matrices in terms of their elements, so using Einstein's summation convention. Whenever two indices are repeated, they are summed over. Once we have done that, we see we just have numbers, and we can take one of these numbers and put it on the other side if we want. So we see that we have A, B, B, C, C, D, D. So that's like a product of matrices. However, the last term is also A, like the first one. So we have a big matrix, and we are summing over elements which have the same line and the same column. Therefore, we are just taking the trace of this big matrix. We can now use one of the properties of the spinors in order to calculate these terms. And remember that the K slash and P slash are using Feynman's notation, and they involve themselves gamma matrices. The trace only acts on spin degrees of freedom, and therefore K and P are just numbers as far as spin is concerned, and they can be taken out of the trace. So when we expand this product of K slash plus M and P slash plus M, we are going to have terms with different numbers of gamma matrices. And we see that we will have to calculate traces of product of 2 gamma matrices, 3 gamma matrices, and 4 gamma matrices. So therefore we need to develop the technology for calculating traces of product of gamma matrices before going further.